Right, thank you, everyone. Not many people interested in Solidity for some reason. Anyway, so how many people here know about functional programming in general? Right, so people actually interested and want to hear this talk. So I hope today I can. The goal of today's talk is to demonstrate the possibility of limited kind of functional programming capabilities in Solidity, and showcase an example of how to use this paradigm to build something called a super token, and also if you are not yet, make you interested in, let's say, functional programming. Right. So a bit about me. I'm Miao. I'm from Superfluid, and very happy to be here. So let's go to a quick example. Right. So this example, the code is into 3 sections, if you will. The first section is the reading data. The second section is transforming those data, like in-memory data. Then the third section will be actually store those data, right? So it's a kind of, for example, of how I would structure so-called a functional programming. And so let's walk step by step to see what I mean here. Is functional programming. So functional programming is a style of programming to describe it declaratively, if you heard of the word. It's basically about defining more what do you want as opposed to how to do it, right? So instead of describe step by step how things should be done, but you describe what should be the effect, right? So in practice, it's about implement as much as the code possible in data definitions, equations, or logical formulas, which would have something called properties. And for this code, what could be helpful is to define so-called strictly pure functions, which Solidity has limited support, which I will mention in a minute. They are your friends because something called a referential transparency, which means same input you will get with same input you will get the same output. So that's one way to put it. With that, it's about deferring the so-called side effects. So what are the common side effects we're talking about here? So like in EVM, when you store access the storage, meaning reading values or values effects. When you interact with the external code, interact with Uniswap, right? And that's actually a side effect. It's external code, group code, for example, like this. Okay. And computation strategy, which is a bit obscure. What do I mean? But that's actually, in effect, computation strategy. Because when you define everything as what, because there's no how component, right? So when do you execute what is actually a computation strategy in the abstract sense, right? So to make the code actually useful, implement the computational strategy is required, right? So most of the language, you don't talk about that because you just mix everything together. It's when you do in Solidity, when you do something equal to something, you're already defining the computation strategy, right? So it's kind of taken for granted. That's why people talk about it much. Typically, it's a sequential, right? In Solidity, you're always dealing with things like sequentially, right? From top to bottom. So that's where the so-called sequential programming. Some people call it monad, a bit scary. I'll mention it a bit later. But if you think broadly, there are different computational strategies, right? About concurrently or graph. It's really good for distributed computing when you talk about things that are not necessarily sequential but parallel, right? That's why there are proponents for UTXOs, because things can be really computed in parallel, like graph computing. And think of a more maybe relatable example. Think of the spreadsheets, right? So in spreadsheets, you don't describe how. What you do, you just define formulas. Things are actually compute as like graph computing in parallel. So spreadsheet is actually a functional program language in a way that it's a massive parallel computing in a sense, if you will. So I describe what it is, but why we do this, right? So some of you might ask. I recommend this paper from John Hughes, really old paper actually, but it's a really short and sweet paper. Describe all the basic principles and to the point, right? So one functional program matters from John Hughes. It's a gateway drug, I would say. One of the sentences I really like to quote is that as the software becomes more and more complex, it is more and more important to structure it well. And well-structured software is easy to write, easy to debug, and provides a collection of modules that can be reused to reduce the future programming costs. Right? So That was something very prescient said in 1989. Fast forward 30 years, right? So the keywords are really about better debug and less kind of cheaper maintenance cost, right? So this is my opinion, but I think I will show a little bit. I think so, but I think it is the best way to structure smart contracts with the limitation. We can still extract as much as possible from the language itself, right? So it is additional right? We all do testing. If we do serious smart contract, we do a lot of testing, and perhaps also limited post-production formal application. Some projects use Chora, for example. Some small scope toy example may use SMC checkers from the Solidity compiler itself, right? But those are like post-production formal verifications, right? But functional programming would be an addition, in my opinion, to these, right? So it allows you to structure the program upfront better as opposed to wait everything compiled and tested, right? So two different approach. I would say it is a good addition for building a better smart contracts going forward, right? So in a way, people like to call correctness construction, but I think we all know that it's people that are in this space in the correctness programming space know that there's such thing called correctness by construction because it's impossible at the moment, at least not easily. So I would like to just call it more correctness by construction. So finally, back to Solidity. So Solidity, well, a disclaimer, there's nowhere near being able to express all the functional programming ideas, but we can emulate some ideas, right? So I'm going to show you a couple of techniques that I think is helpful for you. So custom types, it's something new that people tend not to like it because of the wrap and unwrap kind of spaghetti code it sometimes it generates. Not spaghetti, but more like a bit ugly, some people would say, right? So, but it is a good abstraction device for you to actually make the type more strong, right? One of the things about functional programming that you probably would want a more strong type system, and custom type is one good avenue for that. And since Solidity 8.19, there's also a support for operator overloading, right? So let me show you an example here. So this is part of the live code that we have at Superfluid, right? So the first line would be defining so-called flow rate. What do we do in Fluid? Define it as int 128. And as you can see, there's a pure functions which are mentioned in a minute. What does it do later? And I define, okay, there's this helper function for adding two flow rates together and return a flow rate. And the last, the other is subtraction. And in Solidity, since Solidity 19, you can do plus this rather bizarre syntax for rewriting the plus and minus. So that makes unwrapping and wrapping less commonplace when you do it. It makes the syntax slightly better. So that's one thing you can use in Solidity. Solidity always does this, they only go halfway, right? So the thing is that you can't mix type. You can't mix flow rate or time, and then if you want to do a multiplication, I can't define a multiply with two different types. All right, unfortunately, right? So I have to kind of define the usual approach in Solidity. You define a library, an internal function. You use, you say that for all the value of flow rate, I have a convenient function dot multiplication for multiplying flow rate and time. There are the custom type helps here. So what is the result of multiplying flow rate and time? Oh, actually, it returns a value, right? So the type actually matches, which is great. So there's something called a strictly pure function. Solidity is pure function, it's not very pure. I'm going to show you in a minute. Pure function is really about a referential transparency, but Solidity is kind of a mix of JavaScript, C++, all the languages, right? So it's actually more similar to JavaScript. When you pass memory in, you can actually modify the input memory while you are calling it a pure function, so it's not really pure, right? So the approach I do, the library that I create is that I always do clone, right? So I make sure that I don't touch the input, I always do a clone, right? So people may argue you're wasting gas, but in this case, I would argue it's probably very negligible. So, but then you make your code more principled. So when I say pure function in Solidity, I say strictly pure. I always clone the input, right? So that's something I would recommend also you to do if you start programming. Another thing some people may be curious is that can we define a more generic or polymorphic, some people may say, version of the clone? Unfortunately, I can't. Maybe Solidity promised something generic programming in the next version, so maybe in the next version I could do that. But for now, I have to define a clone function for each data type. So it's a bit of boilerplate, but it is what it is. So we have two functions, strictly pure functions in this case. One is return a real-time balance when you give the inputs and the time, and you can calculate, multiply the flow rate with time minus the delta time and plus the set value, blah, right? So you get a pure function version of the real-time balance. And there is a settle function which you take the input A and you clone it and you do some calculation, and you set some fields and you return the new value, right? So all these are making sure that you don't touch the input ever. You always clone and return a new result, right? So that's the Solidity. The last thing is something that you can also use in Solidity is function pointers, which is a feature that not really people using a lot, but I have actually a very good example of how you can benefit from it, right? So in this particular case, I do it for the test generations. So I define make it better in Solidity, but that's what I end up with. So I don't know what's the input operations, but I just define function pointers. So this is my test templates, right? So I do some operations and do some assertions, blah, right? So now I can generate 4 different tests with a few lines of code, right? So I just provide, okay, I need a shift operation for both OP1, OP2, then I mix flow shift, and shift flow. So all the components in a way. Generate basically 4 different test cases using this data function. And I forgot to mention I'm using Foundry here, right? So it's actually the Foundry generated the random inputs here. So none of these I'm specifying hard-coded values, but you can generate all the test cases like this. So now I give you the overview of what building blocks you have in Solidity that you could utilize to make your programming style functional. So what's a playbook? How do we actually do it? Do I have time? Yeah. Okay. So let's do a step by step. First, define data. Well, this is trivial. You just define a struct. And you also want to define a clone function, as we said before. So for each struct, you have a clone function. Now we don't have MM copy, so we have to do this kind of bit silly way of doing it. Then you call a function that is transforming those data structure you define, right? So you define strictly pure functions in Solidity. 2 examples. One is shifting value from shifting value from A to with the value input X. So you just do the plus X, right? So input, clone, do some calculation, return a new value, right? So never touch input data, like a mantra. Now when you do the flow, it's the same. In this case, you just change the flow rate to a new value, right? So these are the strictly pure functions you can implement in Solidity. Okay, step is that you find these so-called properties so that you can test for, right? So now you define a bunch of functions. How do you know if it works, right? It's really property-based, if you're familiar with the concepts. So what are the properties? Usually there are the mathematical laws governs how these functions work together, right? And tested through the properties testing. Foundry has good support now, right? So you can use Foundry fuzzing test framework as a way to test that. I'll give you some examples. For example, I have the function I showed you. I want to have this 2 formulas always satisfied, right? So I settle twice, and I settle once, and I check the timestamp. They should match T1 equal to T1. And I settle twice with the same T1. They end up the same one, right? So these are another property. How do I know I have a function that works? I use Foundry. I say, give me some random P, give me some random value, and I do this settle and check if that works. Great. So that's how you test that in Foundry. You hard code anything you test. Everything they can randomize you for. Another example would be something seemingly very trivial, but it's important to test trivial things so that you can build stuff layer by layer, right? You don't miss any. You don't want to miss anything. Sometimes it's very expensive to debug all the way to the bottom, right? So in this case, seemingly trivial, associativity law, how to call this? Append to B, append to C equal to A, append to B, to append to C, but with different brackets order, right? So how do I test? I say, give me some random generated data structure, P1, P2, and somehow this is truncated, I think C, right? So A, B, C, and I do assertion say, if I append them in different orders, the value should be the same, right? So that's how you test it with different brackets, and they should always match. Now you have something you can trust to build something on top of it, right? So, okay, so now we have a beautiful function. Don't really do anything, right? You don't store anything. They don't have a sequence of when to call which one, right? So now the last step is to stitch everything together using side effects, right? So side effects, I talk about things like interact with code or storage or access or stuff. Right? So, so the M word is, you are familiar with functional programming. There's a word that no one can explain. It's almost like a joke. So no one managed to explain what is monad, right? So, but one use case I want to mention that maybe help to understand is monad is just a way of highly reusable code for side effects, right? So, yeah, so a way to emulate concepts of monad in Solidity is to use something called an abstract contract. I think everyone uses it, but I use it in a particular way to emulate the idea of monads, right? So the first step would be creating virtual function. So how do I know what side effects I want? Well, the solution is that you don't. So you define it as a virtual function. So you leave to the implementation to define what are the side effects they want to actually influence, right? So you leave it at the virtual functions, and then it has to be abstract contract also, right? So the second step would be actually implement the effect for function that call those virtual functions. So in this particular coding style, you say, okay, I want to retrieve some data. They are calling those virtual functions. I have no idea what those functions are actually in the actual implementation. It doesn't matter to me, because all I want is, when I have those data, I call the data transformations. Remember, these are the pure functions, right? So I get a new value for A and B. Then I apply the updating side effects as the storage update, right? So read, calculate, store, right? In this case, I store something called an index and store the flow value and done, right? So I have a effect for function which leaves all the side effects deferred the definition to the virtual functions. So that's one way to emulate so-called the monads in this case. It's just fancy word for how to stitch everything together in sequence, right? You sequentialize the strategy. So recap. So what you need to do for this coding style is to define the data, define the strict pure functions for the data, you find properties and write tests for them. And Foundry provides a very good framework now. I think I just switched to it for now. Maybe in the next year there's some new tools, who knows. But last step is stitching everything together with a strict separation of pure function side effects. So that's what you want. One way I would recommend is to create the abstract contract. There's other technique which I would not mention in this talk, something called automatic effects. But if you are in that kind of thing, we can talk separately. So can I use it in production, right? That's kind of misspelling rather. Can I use it in production? Yes. And I'll give you an example. So in Superfluid, we have something called a Super Token V1, the version 1 of the protocol. It doesn't use this because it was years ago. If I would start now, I would do that, right? But for the upcoming new feature, which is called a GDA, which I should explain what is GDA here. In essence, it's a one-to-many stream of money, so you can actually stream to any number of participants in the on Ethereum. And GDA stands for General Distribution Agreement. All right, so we have also a V2 implementation of Darknet. It's Solidity, right? So it's Cairo V0, which is funny. They have V1. Yeah, right, anyway. So the V2 is a Starknet prototype using this pattern too. So kind of demonstration that this technique actually is universally applicable. No matter how crappy the language is, you can always emulate it to some extent. So if you try. The V2 version of A token for EVM will be built from scratch using this paradigm, right? So can we use it in production? Yes, because we are going to be production soon, at least for the first feature, right? So we're going to have that. So that's it. Thank you for listening. Let's make Solidity code better, right? In some if you want to find the slides deck, you can go to our repo, Superfluid Finance Protocol monorepo, wiki area. You should be able to find the slides by searching functional Solidity. Yeah, thank you. If you have questions, happy to answer.
Sorry, will check the other mic. Yes. Yeah. Yes, it's working now. Yeah. Switch mics. Sorry.
Thanks. Thanks for the intro into the new features of the Solidity for the functional programming. Anyway, was there or have you seen any analysis or insights into the gas costs of those features? How they are actually rendered into the bytecode, and whether it's worth to use it comparing to the, let's say, the older approach?
Yeah. So the strictly pure functional part of the language, so the concern would be you are cloning the input data, in-memory data a lot, maybe unnecessarily clone, right? So I did a little bit of measurement. Of course, I can't say there's no overhead, but there's a little bit of overhead. But in the grand scheme of things that we're talking about, probably 50 to 200 for each. Actually, cloning is much cheaper. So my claim is it's insignificant in the grand scheme of things. And I would even say that I have proof that this way of programming actually made the program generally look shorter, right? So I don't know if that actually translates to less gas costs per se, because the way you organize program is slightly different. But I would say that it at least doesn't raise a yellow flag or alarms that it's kind of wasting a lot of gas. So no, I don't think it's a problem. Yeah.
And the size of the contract?
The size of the contract. Again, I haven't done a numerical detailed analysis, but nothing alarming. Raise is actually probably even shorter. But it's shorter than the one we have in production, is rather because it's not fully featured yet, right? So there's certain feature gaps. So I can't really say at the moment. So if I want to compare, I would compare apple to apple, right? So I can't compare to apple to orange. So, but there's no alarming yellow flag to tell you that, okay, the size is going to be explosive. No, actually, it does make code shorter, instinctively speaking. I don't know if that actually translates to better. I don't know.